Hello everyone, Students Teach Orgo back again, today with a video on nucleophilic aromatic substitution. I'm going to break this video up into three parts. We'll start off by talking about the addition-elimination mechanism for nucleophilic aromatic substitution. So I think the best time that we're introduced to a new reaction type, it's best just to see an example. In this reaction, this thiolate anion is going to be, it's a nucleophile, right? S- is usually a good nucleophile. It's going to attack the benzene ring and displace this chlorine. So you know the whole video with electrophilic aromatic substitution, it was the benzene ring that was attacking an electrophile. In this case, we have a nucleophile that's going to be attacking the benzene ring. Now, I'm sure some people would be tempted to think that this reaction would proceed with a mechanism where maybe the sulfur attacks that carbon and then the chlorine leaves. But that is not going to be good. And why? Well, if you remember from the SN2 video, SN2 reactions work very, very poorly when the leaving group is on an sp2 hybridized carbon. So if that's not the mechanism, what is it going to look like? Well, if I told you that the chlorine isn't going to leave immediately, that means we're going to have to move this double bond somewhere and introduce a negative charge somewhere in this molecule. So if we go forward, the reaction is actually going to proceed like this. The sulfur is going to attack that carbon, the double bond is going to move over, and then this double bond is going to move up to put this minus charge on the oxygen. Now this nitro group, right, NO2, is a very strong electron withdrawing group, which is the only reason why this reaction works. If this electron withdrawing group wasn't here, we would have had to put the negative charge on the carbon like that and make a carbanion. And those are usually no good, not very stable. That reaction wouldn't go very fast. But by having this electron withdrawing group right here to take up that negative charge, this reaction proceeds fairly quickly. Now, once we get to this intermediate right here, we're not quite done, because if you've noticed, we've broken the aromaticity of the aromatic ring. So the only logical thing to do is then take that negative charge that we just put on that oxygen, bring it back, and reform our benzene. And that is going to look a little something like that, where we start with the minus charge, come down here to remake the double bonds, and that arrow will move here to remake benzene, and then we finally kick out chlorine, which is our leaving group. So a good phrase to think about how the addition-elimination mechanism works is that we're going to park that negative charge on the electron withdrawing group and then swing it back to kick out whichever leaving group we had on our benzene ring. So, an important detail that I didn't mention is that the leaving group and the electron withdrawing group have to have a particular relationship in order for nucleophilic aromatic substitution to really be efficient. And so what I've done here, I know it's a bit of a busy slide, is I've given you that same example that we looked at previously, but with an ortho relationship, para relationship, and meta relationship between the leaving group and the electron withdrawing group. Now, what I want to point out is that when the nucleophile attacks, right, and you have this negative charge here, that negative charge is being shared between three carbons. That negative charge is there, that negative charge is there, and that negative charge is there. To give us something like this, that delta minus 1/3 just means that there's a partial negative charge on all three of those carbons once the nucleophile attacks. Now, the only way for this reaction to proceed at a relatively fast rate is for us to have the electron withdrawing group on one of those carbons that has the negative charge. So what does that mean, right? So you can see over here, when the sulfur attacks, right, we can put that negative charge on the electron withdrawing group. That works. And when the electron withdrawing group is para to the chlorine, we can also put that negative charge on the electron withdrawing group. That's cool. However, when there's a meta relationship, you'll notice that we can't draw arrows in a way that will put that negative charge on that oxygen group. So that is not going to happen, or at least it's not going to happen very quickly. So we need an ortho or para relationship between the electron withdrawing group and the leaving group in order for addition-elimination mechanism to work. So now let's think about what happens when there's more than one electron withdrawing group. And I think this makes a lot of sense. If you have one electron withdrawing group, and in this case they've drawn it in the para position, so this is one of those positions that can help stabilize that negatively charged intermediate, you can see that that'll proceed relatively fast, but it'll go even faster if you add another one in the ortho position here, and it will go even faster if you have both of the ortho positions and the para position filled with electron withdrawing groups. Now keep in mind that this reaction probably wouldn't go that much farther if you'd added an electron withdrawing group in the meta position. It's really only in the ortho and para positions that electron withdrawing groups are really going to increase the reaction of NAS significantly. Another trend that we have to think about when thinking about the reactivity for NAS is that the leaving group can determine the speed that the reaction will go at. So you can see here that iodine, bromine, chlorine, fluorine, these are all of our halogens, and you can see that fluorine is actually going to result in the fastest rate of reaction, which is kind of confusing because normally when you think about carbon-fluorine bonds, these bonds are relatively hard to break. But we can rationalize this by saying that the fluorine is the most electronegative atom on the periodic table. So in this bond between the carbon and the fluorine, the electrons are going to be hanging out by the fluorine more than they're going to be hanging out by this carbon. And that's going to give this carbon right here a partial positive charge that I've denoted with this plus delta, which means that when the nucleophile, like I'll use that nucleophile we were using before as an example, the negative charge on this nucleophile is going to be more attracted to this position right here than it would be for chlorine, bromine, and iodine. So that brings us to our first practice question here. I want you guys to try to order the following molecules in respect to increasing reactivity in the addition-elimination NAS reaction. So take some time. This is a good practice problem for free. Pause the video. I'm going to go on and explain the answer here. So this is the order with this molecule right here being the most reactive and this one over here being the least reactive. As far as the logic that I would use for determining that order, right? I would look first and say that, well, this is the only one that's got 3 electron withdrawing groups, and those 3 electron withdrawing groups are all in ortho or para positions. So immediately I would say that B looks really good for being the fastest. So I guess I'll write that right there. And if I were to keep on looking, I can see that this compound here, A, and this compound over here, E, both have 2 electron withdrawing groups, and the electron withdrawing groups are in ortho, they're both in ortho positions here, ortho para here, so equivalent as far as electron withdrawing groups go. But if we look at bromine versus fluorine, fluorine's going to be a better leaving group in this case. So that would be our second fastest, followed by this one in third. And then comparing C and D, these have electron withdrawing groups in the meta position to the chlorine, right? That's a 1-3 relationship. So these electron withdrawing groups really aren't doing anything to enhance the speed of this reaction. And if we have to choose which one's faster between C and D, iodine is the worst of all of the leaving groups, so that's got to be last, or the slowest. And this one's got to be fourth, I guess. Right? And so then I would just, take that logic like I explained over there and make this answer. Alright, let's jump right into the next practice question where we have to synthesize this molecule starting from benzene. In our electrophilic aromatic substitution video, we learned about a reaction called Friedel-Crafts acylation. So putting on this acyl group attached to the benzene ring should be pretty easy using what we learned in that video. However, we haven't learned of a way to put on a group that looks like this. So, using NAS, we should be able to figure this out. Now, the question says that we have to start from benzene, so there's our benzene molecule drawn out right there. Our first step should be using Br2 FeBr3 to substitute one of the hydrogens on the benzene ring with a bromine. And remember, this reaction was talked about in the electrophilic aromatic substitution video. The next step is to do that Friedel-Crafts acylation that I was just talking about. And bromine being an ortho-para director, we can assume that this para product will be a large product. You might get some where the Friedel-Crafts acylation occurs at the ortho positions, but for all intents and purposes, this is a relatively good synthesis, and we can put the acyl group down there. Now, the last step is going to be the nucleophilic aromatic substitution step, where we use methoxide as our nucleophile. Methoxide is going to attack that carbon right there, and the whole point of putting on this group down here is that this is an electron withdrawing group. So we can move the electrons all the way onto oxygen, oxygen will have a negative charge, and then it'll kick it right back, reverse all those arrows, and bromine will leave to give us the product that we were asked to synthesize. And here is a third practice question. In this question, we have to predict the product and draw a mechanism. Now, this is the first time in this video that I have shown you a molecule that has more than one leaving group. And so the hardest part of this problem is actually the very first step, where we have to decide whether this nucleophile here will attack this carbon, or this carbon. Now, if you remember from earlier in the video, in order for the electron withdrawing group to enhance the rate of the reaction, the electron withdrawing group has to be ortho or para to the leaving group. And as you can see here, this bromine and this chlorine are both meta to the electron withdrawing group. So by far, the best choice of carbon for this nucleophile to attack is that carbon right there. And so if I draw out the arrows, the hydroxide attacks that carbon, which means we have to move that double bond, put the negative charge on the oxygen. We get to here. Then we do all those arrows in reverse, just as I've shown you before. We kick out that chlorine, and that gives us this for the predicted product. In this next part of the video, we will discuss the elimination addition mechanism for nucleophilic aromatic substitution. Just as before, I think the best way to be introduced to a new mechanism or reaction is through an example. So these are the reaction conditions that you're normally going to see for this elimination addition mechanism. Now this reagent up here is a little funky. You haven't seen it before. This is called sodium amide. It's an ionic compound. You can imagine that the electrons in this bond are going to hang out with the nitrogen, so that we can actually think about this as just sodium plus and NH2 minus. Now nitrogen normally doesn't have a negative charge because this is a very, very reactive compound and a very, very strong base. Another thing I'd like to point out is that in this case, our benzene ring no longer has an electron withdrawing group on it. So if we were to think about a mechanism where this N- attacks this carbon right here, that negative charge would have to be stuck on one of these carbons down here and create a carbanion, and generally that isn't super favorable. So there's going to be a different mechanism this time, and I'll show you how that works. The N- is actually going to pull a hydrogen from the benzene ring. We're going to move the electrons between that carbon-hydrogen bond to form a triple bond in the benzene ring, and then that leaving group will leave. Now this creates a really weird looking intermediate called benzyne, where benzyne has this alkyne in the middle of this benzene ring. Now you might think that this is horribly unstable, and it is pretty horribly unstable because of all the ring strain here. These sp carbons usually like to be linear at 180 degrees. But what's interesting is that this still keeps its aromaticity because one of these double bonds is outside of the pi system, so you actually can form some product that looks like this. You can't store it in a bottle, you have to make it like in situ, which means you have to make it while the reaction's going. But once we get to here, this incredibly reactive intermediate is going to want to react with something else in solution. So we have another N- come in. This N- is still very nucleophilic. It can attack one of these carbons, put that negative charge on the carbon, and that carbon's immediately going to reach out, grab a hydrogen from some of the ammonia that it's floating around in, and you will make the substitution product. Now, some students ask the question, and it's a very good question, well, why can't ammonia be the nucleophile that attacks the benzyne intermediate? And that's certainly the case. That can certainly happen. So I've just redrawn what I drew up here. But in this case, we have ammonia attacking the benzyne instead of NH2. And if that happens, once ammonia attacks, it's going to take on that plus charge. That carbon will just pluck a hydrogen from it, and we get the same product. Now, I want to make it very clear that both of these mechanisms are correct. And if you're taking a test and you use either one's good. Some people like this one more because the N- is super reactive, so they think that this would be the molecule that probably more often attacks the benzyne. But the solvent is this ammonia. So if there's more solvents around, it's just as likely that this ammonia could attack. And either way, you get to the same substitution product. Here is our fourth practice question of the video. Which of the following molecules is unable to react in elimination substitution NAS? Now I haven't explicitly given you a rule for which molecules are unable to react, but take your time, pause the video, think about the mechanism that we just talked about, and which one of those molecules wouldn't be able to perform that mechanism. Alright, I'm going to go forward here. The correct answer is going to be B. And the reason why B would be the only one unable to react in the elimination substitution is because B doesn't have an ortho hydrogen. You need an ortho hydrogen to the leaving group, right, to the bromine in this case, in order to make that benzyne intermediate. We can't form benzyne on either side here because of these two methyl groups. So no reaction occurs without the ortho hydrogens. B would not be able to perform the elimination substitution NAS. For the next practice question here, I'm asking you to determine how many unique products are formed from the elimination substitution reaction and to draw the structure of each product. This is a longer question, so definitely pause the video, really think about it. I know in the first example, I used a reaction in which there was only one product formed from the elimination substitution NAS. But if you think about the mechanism, there are a few opportunities for different molecules to attack different places, and that can create unique products. So think about it. It's a very good question, and I'm going to go forward. So the first thing to think about is that we have a hydrogen on either side, and this NH2-, does it have a preferred hydrogen that it wants to attack? Would it go for this one, or would it go for this one? And the answer is it has no preference. It can attack either one of those hydrogens, and either one it attacks, it can make the benzyne intermediate after kicking out chlorine. So let's show what that looks like. Right over here, we have the nitrogen grabbing that hydrogen, making a triple bond here, kicking out chlorine, and over here, it's taking that hydrogen, making a triple bond, kicking out chlorine. Now, I do want to just point out, because some students get a little tripped up by this, over here, right, they'd be like, how can that nitrogen grab that hydrogen? Because if I go like that, there's no triple bond there. And the important thing to remember is that benzene you can draw with the double bonds alternating any way you'd like, right? Here the double bonds go like that, down here they're like this. Both of them are the same, right? These molecules are the same, but drawing it in a particular way can make it easier to draw your curved arrow mechanism, taking off one hydrogen or the other. So that's just a quick note I wanted to draw here. Now the reason I've drawn this twice is because I'm going to draw two different paths now based on the benzyne intermediate formed here and the benzyne intermediate formed here. Alright, so here are the benzyne intermediate products. You'll notice that over here the carbon attached to the methyl group and the triple bond are right next to each other. But over here there's a carbon in between the carbon attached to the triple bond and the carbon attached to the methyl group. So this already has two unique intermediates, and we'll see where that goes from here. Now ammonia is going to attack the triple bonds. But here's another question. Will ammonia preferentially attack this carbon here or this carbon there? And for down here, will this ammonia preferentially attack that carbon there or that carbon there? And the answer, again, is that there is no preference. Ammonia is just as likely to attack this carbon as it is this carbon, and down here it's just as likely to attack this carbon as it is this carbon. So let's draw out the next stage of intermediates. If ammonia attacks this carbon specifically, we move one of those pi bonds over to this carbon, and we get an intermediate that looks like this. Over here, we attack the other carbon on the other side, and then you can see I've done the same thing down here. And that gives us these four intermediates. In the last step here, I'm just going to have that negative charge on the carbon grab one of the hydrogens to create our neutral products. And you can see that we've created these four different alternative paths. Now the question asked to identify how many unique products are made. And so over here we've got a 1,4 relationship between the NH2 and the methyl group. Over here we've got a 1,3, down here a 1,2, and here it's 1,3 again. So we've really only made 3 unique products, and the structures are these right here. In this last part of the video, I'm just going to talk about some different ways to generate benzyne. In the last section, we saw that with that really powerful base, right, the sodium amide, we could pluck a hydrogen, have a leaving group leave, and that made benzyne. But there's a few other ways, and they could be tricky and have a mechanism or synthesis question in which it's better to use some of these other ways. So let's take a look first at this reaction. You can generate benzyne by making a benzene ring that has an ortho relationship between a bromine and a fluorine. In Orgo 1, we learned that bromines, when magnesium is present, can make a Grignard reagent, and this Grignard reagent we used in Orgo 1 to use as like a synthesis to make carbon-carbon bonds. But it also turns out that the magnesium and fluorine are relatively attracted to each other. So following a curved arrow mechanism like this, we can generate benzyne, and we can use that benzyne to go forward with a nucleophilic aromatic substitution reaction. Another example of a different way to make benzyne is this crazy compound here, where it's actually an amino acid, where we have the carboxylic acid here and the amine here, and they're both attached to benzene. Now, in Orgo 2, up to this point, you haven't learned about this reaction right there, but you will soon. And what it does is it creates this diazonium ion from this amine attached to benzene. Now, N triple bonded N is the same thing as nitrogen gas that's like floating around in the air all around us. And this is a very, very stable compound, very, very good leaving group. So we can take the electrons between this oxygen and this hydrogen to make a double bond here. This bond right here is going to break, which will release CO2, seen right there. We make the triple bond, and in making the triple bond, N2 is our leaving group, and like I said before, it's a very good leaving group. And so following something like this, we can make benzyne in this fashion. Alright, so here's another practice question. In this case, I'm giving you the entire reaction, right? I'm showing you the reactants, I'm showing you the products, but I'm hoping that from the previous two examples that I've showed you, that you can kind of extrapolate how the mechanism works and show me the curved arrows that would go on in this benzene and anhydride to create those products. And so the answer here is you can see that if we have this bond move over here to make a double bond, we break this bond and put a negative charge here. That's going to generate carbon dioxide between those two carbons, right? So that's going to be this guy. By putting the electrons from this bond onto that carbon, that's going to make hydrogen monoxide over here. And then we take that bond that was between this carbon, and we can generate benzyne. So that's how you'd go about drawing the curved arrows to show the formation of this. And then last but not least, this is another practice question. That's a good example of how they could ask one of these generation of benzyne questions on a test or something. So they give you 5 different reactions here, and they give you a starting product, and we have to figure out what the final product is. I highly recommend pausing the video here, thinking about it. I think this is a very good practice question. Alright, I'm going to go ahead now and just show the entire answer. We would expect to make this product from the mentioned series of reactions. And so let's look at this more step by step now. Right, the first step is sulfonation, which we learned about in the electrophilic aromatic substitution video. This is going to put a sulfur group onto the benzene ring, and the fluorine is an ortho-para director, so we can assume that a lot of our product will have this sulfur in the para position. And we're putting on the sulfur. The reason why it's important is because this sulfur will now act as a blocking group to block the addition of bromine in the para position. And so now we're forcing this bromine to go ortho. Now that this bromine is in the ortho position, we can take off the sulfur group. Remember that the sulfonation reaction is the only one that's reversible by using some water and dilute sulfuric acid. And then we get to here. And remember, this is the starting point for that example I talked about a few slides back for making a Grignard reagent to create benzene. So we put in some magnesium, we create the Grignard reagent. This will follow that curved arrow mechanism I showed earlier to create benzyne. And now, this last step, right? Benzyne, or just alkynes in general, are good dienophiles in the Diels-Alder reaction. And over here, I've given us a diene. So with a diene, and down here we have the dienophile, we can go forward and proceed with a Diels-Alder reaction. And if you're not familiar with the Diels-Alder reaction, we have a YouTube video on this channel that goes very in depth. But this would be the product of that Diels-Alder reaction with benzyne that you would expect to get. Alrighty, that's all for nucleophilic aromatic substitution. I hope that helps.